Glass, as you may already know, is an important part of our architectural work, the idea of transparency in the buildings and shapes we create. And the start of this presentation is really to get us to start thinking about kind of the mechanical systems that hold the glass up, the kind of uses that it has. So I'm going to show you a bunch of slides, talk a little bit about it to get us stimulated on that thinking. So here we have, and a lot of these are hyperlinked, so if you open up the actual slideshow, you can go to these projects. So the first one I wanted to show you is just this idea of all the many kind of applications of glass. So here we're using it as actually a roof system in a public venue. So there's many times where architects will be busy specifying these kind of systems and in very creative, innovative ways. This is probably one of the more popular or talked about facades. This is a double wall facade, and the idea of using parametric design to fragment or fractally represent it. Very complicated type of system, and I think we'll talk a little bit more about this later. So I guess maybe to elaborate a little bit, this is actually a mullion system, and we'll talk about that a little later on, but we have the idea that the glass is supported at its edge conditions, and why I'm saying that is because here we have now other kinds of support systems, and each one of those has their aesthetic to them, their value systems, their cost, and this is really kind of what we want to pay a little bit of attention to going forward with the next module, the one that comes after today's module that we'll be working on. So one of the big movements in contemporary glass is the idea of using it in innovative structural ways and using larger panel sizes. So we're really starting to engineer very high performance glass and of large sizes, so there's a lot we can accomplish with it. Here's a great example of a system of using glass as a structural system, a glass stairway, and really extraordinary amounts of feet of carrying load through the systems. So here we have, you can imagine this guy cantilevered out over this, what looks like a very lightweight glass system or fragile glass system. And you can see what supports it here. You can see this transverse element here. This is a beam coming out, cantilevered out from the wall, that's supporting the front part of that deck and the two ends of the stairway. And then the back side is supported by the edges or the side walls of the stairway. But we have a very rigid structural system that's also transparent. And these are hyperlinked to a presentation. One of the leaders really stimulating the industry both from the architectural standpoint and the product standpoint is Apple and their utilization of glass. They really pushed vendors to the limits of what they can produce as glass. Steve Jobs, before he died, had envisioned these large, it's their headquarters in Cupertino, but these large glazed panel systems that surround their headquarters building. And you can see this is an illustration of the size of those panels, 46 feet long, 10 foot 6 inches tall. So these are some of the largest glass panels manufactured, I believe, in the world. And Apple has had a fascination with glass. Their iPhones, the screens on them are made out of what's called Gorilla Glass, high performance glass, and they really incorporated glass to an extreme in their architecture of their stores, their flagship stores. This is a new one in Chicago, not so new now. If you cross the river here, we can see this idea of transparency that looks like the lid of a computer floating on top of this glass panel. And we can see from a little closer up, we have these large curved panels, and this is actually the short one. We'll see one now that is on the other end of the building in another view. But this idea of transparency, of the glass carrying structural loads, really doing an amazing amount of performance to both aesthetic performance and structural performance. So here we have that other end in this large piece of curved glass, what appears to be supporting the roof. And it's time to start paying attention to some of the beautiful details. Here we have the glass really kind of crashing into the floor plane. There's no support structures that come above the glazed area. So it creates a very seamless, transparent feeling. but it's not without a great deal of work. So here's close-ups that I took of the glass. What I'm trying to illustrate here is that this is not a single thick piece of glass, but it's made up of multiple layers of glass. So we have 3 sheets of glass fused together. Here's another section where it looks like we have 4 sections of glass fused together. This is a door. This is probably one of the main panels of the structure. And beautiful articulation of details, right? So we have the glass, the handrail supported with nothing coming down. It's supported right into the glass structure. And look at how the mirrored stairway with the glass coming right between them and going down below the ground plane. Lots of technical problems come with this kind of creation of transparency. And for instance, here we have a door. We've got a large panel above it. The door has to be able to move that load to the sides, to these vertical columns. So there's a lot of structural capacity that has to be built into these door frames. It'd be very difficult to put an all-glass door into this system because there'd be nowhere to place the transfer the load. So then, the architect's goal here is to really make this look as elegant and lightweight as possible, which I think they accomplished. Another feat when you start to move into this idea of transparency are things that seem to be very difficult to create transparency, like an elevator with all of its mechanisms, and they managed to do it very elegantly here. So we have a cab that's made out of glass. But even the mechanisms, the doors, all hidden mechanisms to open it, quite an engineering feat. The vertical transportation elements, all hidden. And they carry this through to the revolving door. So this top piece of circular glass, structural to support the frame system, the curved glass on the side edges, all of this tremendously expensive, and they're not the first people that have done glass doors. You'll find these around, but part of that whole project. So you can also not just think of glass as a flat planar surface. Now I've got a couple of examples of what can happen when in manufacturing you form that glass. Channel glass, as this is referred to many times, is a unique way to use glass in facades. This is an example building, and I have this hyperlinked. But here we have channel glass really making up the whole facade of the building, and then this idea of that transparency allowing it to become part of an illumination component at night. And form glass has another methodology. It's called slump glass. This Nike flagship store is used kind of an iconographic effect in the glass. Part of their design motif, and it's called slump glass at this point, where the glass is allowed to fall into a form to create its shape. And I picked up this detail because I thought it was very nice, but also it shows you this idea of the slump glass actually coming up to a flat area so that it has a common way of mounting. So formed glass. Silicone is probably one of the most important things that makes a lot of what we see possible. The ability to seal, to structurally hold in place, and to transfer loads between the glass panels. And why I say silicone is because it is a really high performance material. It is the go-to material when we talk about glazing systems. This is a Dow Sealant presentation that I stole some slides from. And we're looking at this idea between organic and inorganic sealant chemistries. And most of these, all of these are high performing, can be high performing, but none of them will be as high as pure silicone. And this idea of carbon-based, organic-based polymers is where longevity issues become critical. And in our systems, we build architecture to obviously last a long time, so this idea of sealants not degrading and failing is critical. These carbon-based products degrade from UV exposure from other organics in the atmosphere, so they can become very problematic relatively quickly. Why are we talking about sealants? Well, in this case, we're primarily, this is a glass presentation, but we use sealants obviously to keep air and water out, and we can use it between any two materials that we need to bring together. And glass and aluminum, glass and glass are typical what we think about when we're working with glass. So sealant properties, obviously it has to adhere to the surface. Silicone has a high adhesion to glass, which makes it really a very effective material to use for just about all applications involving glass. This idea of a modulus of flexibility in that material, allowing for movement, and so it doesn't damage itself, and that movement capability between the rigid materials, the glass and the aluminum, and in some cases having different coefficients of expansion. By that I mean the aluminum will elongate at a different rate than the glass will as the atmospheric temperature changes. And we don't want those two differences to not be able to be absorbed by the flexibility of our sealant. And then durability we really kind of already covered. Now, I'm going to cover a few slides about this idea of how these materials get adhered together with silicone. But I think it's important both for the idea of the architect as the site inspector, but also the one who details drawings. And drawing these correctly and understanding the implications of the way they're drawn are really critical to effective project management. 1/4-inch contact surface areas, important. This 2-to-1 depth ratio, important. Avoiding 3-sided adhesion systems and using backer rods or bond breakers. So in this case we have what could be 2 pieces of stone or 2 pieces of glass. This is the backer rod, the idea of, so we don't create a very thick amount of silicone. We don't want it to go larger than it needs to, but we always want to have this kind of an hourglass type of joining between the elements whenever possible. So here we have a large adhesion area, and then a very small area, neck down area, this kind of an hourglass shape, and then the second adhesive area, very large. So the idea here is that if we were to pull these two apart, we have a large surface area for an amount of force, and right here we have a minimum amount of surface area for a large amount of force. So when load is applied, this is the area that's going to do the stretching. And we want that to occur there. We don't want it to occur at the edges because we want these to stay intact under load. So we don't want our bond to fail. We want our silicone itself to fail under extreme loading, which really does not occur because these are really significantly overjoined. The amount of forces to pull it out are forces that it would typically never see. So we've already stated all of these. One of the important points that I realized is this idea of large joint widths, and that'll come up in a couple of more slides. So here we have this idea of not too much sealant in it. So we have these kind of dimensions, at least 1/4 of an inch. The A dimension must be at least 1/4 of an inch. That's in order to create this kind of right ratio between a thinned area and thickened area, so we get the right kind of performance with it. Typical corner detail where we would want to join maybe structural glass. And so here we have this poor joint design, no bond breaker. We don't form this hourglass shape here, as you can see going on. So if we don't do it, we get this kind of joint, and this becomes very rigid in here, and the likelihood of joint failure at the edges goes up. And then this idea of a bond breaker in here. So we're not adhering at more area, and in this case it's not 3-sided, but it would be 3-sided if it was another element. Probably more detail than we need to get into in this introductory part of it, but some ideas of effective joint design. You can notice there's a little bit of a well, these are really just too subtle at this point. I would like to maybe point out what we're looking at here. These are 2 pieces. This could be a thermal pane glass. It looks like this is the sealing between a thermal pane, 2 pieces of glass, and this is typically a polymer that supports the load of the glass, transfers it to the aluminum frame here. The compression gasket pushes this tight to the front of the frame. where there's other gasketing material here, and then this idea of in order to seal this enclosure from water intrusion is the application of the silicone cap bead. And the sponge gasket is actually breaking the bond, not creating a rigid bond, three-sided rigid bond here. Let's see if we can point out anything here in the failures of the systems. So here we have too small a gap, or too small of surface area. This is under 1/4 of an inch, and I think that's probably, and then gray sealant is prone to discoloration. I'm not exactly sure what that's talking about there. This is the idea of being able to cover large areas. So here we have two pieces of glass coming together, not touching each other for good reasons. We wouldn't want to transfer, we wouldn't want hard on hard between glass because of the potential for shattering it. But we have a 1/4 inch and 1/4 inch bond between them, and probably a tape was applied in order to create a way to support that silicone while it was applied. The last slide here on silicone is about this idea, why I picked this up was this idea of permeability, this vapor permeability, the idea that moisture can move through the elastomer in order to allow things to dry out, but water can't move in. So if water is already in or gotten in some other way, the silicone has vapor permeability to it to allow things to dry. And that will take us to part B.